In our last video, we used GPS to examine a simple desktop calculator project to figure out how it worked. We were able to compile, run, and use the program, but for some reason, anytime we tried to print a matrix, garbage characters would be displayed. So in this video, we'll use the GPS debugger to get to the bottom of this. To fire up the debugger, go to Debug, Initialize, then Your Main File, which for us is SDC. The screen will reconfigure itself and adopt a different perspective with panes useful for debugging. What we call the GPS debugger is in fact a graphical interface to an underlying debugging technology. Downstairs in the debugger console view, you can see the telltale prompt that suggests that we're using GDB as our debugger engine. On the right, you have a call stack, as well as some data displays for breakpoints, debugger variables, and locations. On the top, some additional toolbar buttons appear for directing the debugger. In order, these are Continue, Step, Next, Finish, Stack Frame Up, and Stack Frame Down. We know that we want to set a breakpoint on whatever it is that prints the contents of a matrix. So, from the main loop's call to process, we'll follow the yellow brick road till we get to processing for the print instruction. Let's set a breakpoint on the line that prints a value. We'll do that with a single click on the number 49. We don't know yet whether there's something wrong with the print function here, namely screen_output.message, or if there's something wrong with the function that converts the value to a string. To start the program, we'll use the menu item Debug Run. You can provide command line arguments for your program here if you like. The checkboxes selected here will make us drop into the debugger right away as our program begins. And, for no particularly good reason at the moment, we'll use the project's execdir rather than whatever the current directory is when running the program. Now we're cooking with gas. The debugger has kicked in, and now we're looking at a pause program about to execute line 9. I don't know if you noticed the black flash, but the program was launched in a separate execution window rather than within a GPS view. I'll move it so that you could see a bit of it behind GPS. Let's get right to the section in question. I'll click the Continue button. You can see the initial text appear in the execution window. The debugger is going to start the program and then wait. As a developer, you'll either be working the application while the debugger's waiting, or working the debugger while the application's stopped. Let's get right to working the application and demonstrating our problem. I'll enter a matrix and print it. The debugger hits the breakpoint, and you can begin using the GPS interface to explore what's going on. On the right, you could see the call stack that gives you an idea of how we got here. From the main procedure, which called tokens.process, which then called instructions.process. Let's step through the program and see where the execution takes us. There are two kinds of single stepping that we can use: step over and step into. If you step over, you stay in the current stack frame, executing the whole line, that you see highlighted here. If you step into and you have a subprogram about to be called, you'll follow the execution into that subprogram. I've always been a command line user, so I'll use GDB commands to work the debugger. The step command will step into a subprogram. After the single step, we find ourselves in the stack code. This code is not suspect, so let's pop out of this. We'll execute the rest of this subprogram and then stop. This is accomplished using the finish command. Stack.top just returned the value at the top of the stack, and you could see the access value that it returned in the debugger console. The next subprogram to be called is going to be the values.toString function. Let's step into this. GDB accepts shortcuts on its command line, so I'll say S to step into the function. The command to step over in GDB is next, so I'll use that to do the next single step. Instead of typing in the whole word, I'll just use the shortcut N. This looks like the actual conversion routine. Using tooltips, you could examine the values that are being passed. V is that access value that we got from the call to stack.top. M is some kind of number, but obviously isn't the 1, 2, 3, 4 matrix itself. Let's step into this print function to see what it does. Looks like an interface to a C function called matrix print. Another step into command gets us into some C code. Looks like more stuff to keep track of. There are multiple ways to display data in the GPS debugger. One is using the debugger variables pane. Well, let's display the row and column variables there by right-clicking on each variable and selecting Debug, Display Row in Variables view. And we'll do the same with column. There's also a graphical data display canvas. To display data there, right-click on our entity, go over to Debug, and we'll select the dereferenced version, star result, to show in the graph. Okay, now that we've got our display set up, let's step a few times. Alright, got some looping action here. You can see that any variables that change value highlight in red in the Debugger Variables pane. This looks like a string conversion to me. We get a numerical value, and then use sprintf to append text to the result string. So, if I single step here, the box in the Graphical Debugger data area should update. Well, that's funny. We saw the row and column variables update as we looped, but there was no change at all in the result string. And now we're about to return that result. And with some more single stepping, we'll unwind the stack and get back to right after our breakpoint. The output in the execution window doesn't look like what we saw for star result in the debugger data canvas at all. Let's try this again with even more instrumentation. There's got to be something wrong with how we're handling that result variable. Let's hit continue and try to print the matrix again. And now we're back at our breakpoint. I know we want to get back to that C function. Here it is again. We can right-click at the beginning of the function and tell the debugger to continue to execute the program until we get to this line. And now I'm really curious about what memory looks like where result is pointed. First, let's get past that malloc where we assign to result. Right-click on result, go to Debug, and view memory at address of result. The memory pane shows up in the workspace where I'd rather see sources. So I'll pop it out of the GPS interface into its own window by dragging the pane out. Now here we're looking at the contents of result, which is a pointer, not the string that it points to. I'll change this to star result so we can look at the string. All right, we're ready. Let's single step. All right, we have a problem here. We're about to append some info to result, but there's all this 0D, F0, AD, BA junk in there. Since this is a C string that's supposed to be empty, it should have a null or a 0 right at the beginning. So that's what's going on. We use a malloc to allocate memory, but we never initialize it before use. So is that true? Let's scroll down in that memory view till we encounter a 0. Okay, there's that first 0. If my hunch is correct, when that sprintf fully returns, the memory view should update where that first 0 is. And there it is. I'm sure that if we continue to single step through this function, we'll be appending the matrix text right there. Just for fun, I'm going to put a null right at the beginning of star result to see the program function a little bit more correctly. You can type values directly into the memory view to change memory. Then, hit Submit Changes to register your changes. And there we have a slightly more correct execution, at least one that doesn't potentially overflow a buffer. So we found the problem. Let's quit the debugger by using the menu item Debug Terminate. We'll clean up a little bit and get rid of the memory view. There are a million correct fixes. One is to replace the call to malloc with calloc, which will initialize memory and also check its arguments to make sure that the arguments make sense. It requires only minor changes. And now, just recompile the project. Small problem here. Permission denied trying to open sdc.exe. This is a common problem in Windows. It means that the sdc.exe file is open somewhere else. Since it's an executable, it's likely we have an execution somewhere that didn't completely terminate. We'll use the Windows Task Manager to kill those processes. Now with those processes killed, the link completes successfully. Let's see if that change from malloc to calloc did anything useful. No more garbage characters. If you're interested in an in-depth treatment of the features available in GPS and GNAT Pro, AdaCore offers a variety of training courses that might suit you or your group. Please contact AdaCore if you'd like more details about our training courses.